Hello everyone, my name is Rémi Delaunay and I'm a PhD student from University College London. I am now going to present our work called an unsupervised approach to ultrasound elastography with end-to-end regularization. Quasi-static elastography, which is also known as strain imaging, is a technique that has been developed to image and evaluate tissue stiffness. This is done by considering the relative displacement between a pair of images before and after applying a force on the tissue. This force can either be an internal compression, such as a vascular pulsation, or an external force, just by pushing the probe on the patient's body, as shown here in this diagram. The displacement estimation is usually made between pairs of radiofrequency data, which correspond to raw beamform ultrasound images, and is often estimated by maximizing a correlation function between local image patches. The strain field represents the relative tissue deformation induced by the applied force. It can be obtained by spatially differentiating the obtained displacement field. Since most of the compression is performed in the actual direction, ultrasound systems often display the actual strain over the beam mode image. The recent application of deep learning methods in optical flow estimation have inspired new approaches in strain elastography. Some of those methods are listed here. They have shown the ability of convolutional neural networks to produce accurate displacement estimates. They also appear to be more robust to noise and out-of-plane motion, as compared with conventional speckle tracking algorithms. Those methods are trained in a supervised way, which means they are using only ground truth labels during the training stage. This need of ground truth labels limits the training data to ultrasound simulation. This is because it can be quite difficult to obtain accurate displacement estimates with real data, since the force applied by the probe is usually unknown. Using only ultrasound simulation for training presents several disadvantages. For example, it can be challenging to produce simulation with complex, realistic image content. Also, they can be quite computationally expensive, because the compression force used to produce the image displacement is computed with finite element methods, and also this limits the complexity of the deformation produced. That's the reason why in this work, we propose a completely unsupervised method that allows us to train our network directly on real ultrasound data. In order to do that, we propose a loss function which is based on the local normalized force correlation, which is a similarity metric commonly used in image registration. Our loss function also includes a regularization term that enforces the strain smoothness. Finally, our experiment suggests that the quality of our strain estimates reach state-of-the-art performance, as compared with the gold standard method. The diagram shows here an overview of our method. As you can see, our network has an encoder-decoder architecture, and it takes as input a pair of ultrasound radiofrequency data that correspond to the reference and the compressed image. The network then outputs a displacement field to match the reference and compressed image. Then this allows us to compute the actual strain using a GPU implementation of the well-known least squares strain estimator. During training, the network parameters are learned by minimizing a dissimilarity metric, which corresponds to the negative normalized force correlation. This metric is computed between local patches extracted from the reference image and the compressed image resampled with the predicted displacement field. The loss function also includes a regularization parameter to ensure balance between the likelihood and smoothness of the predicted transformation. Here we use the L1 norm of the strain map gradient to enforce the smoothness of the prediction, which also corresponds to the second spatial derivative of the predicted displacement field, and therefore we can use it during training. The performance of our method was assessed using two different experiments. The first experiment involved training our model on ultrasound simulation and comparing the results with three other strain predictions. This included the ground truth strain labels obtained from finite element methods. And we also wanted to compare our unsupervised training strategy with a supervised one. Therefore, we used the same network architecture than in our method, but we trained it with a supervised loss function. This loss function corresponds to the mean absolute difference between the network's strain prediction and its ground truth label. And finally, we compare the performance of our approach with the overwin methods, which overwin stands for total variation regularization and window-based time delay estimation. Overwin is a non-learning based method developed by Mirzai et al. which uses a classic patch-based correlation method but combines it with a regularization-based approach. In the second experiment, we train our network exclusively with in vivo data, and therefore compared our results only with the overwhelm method because of the lack of conscious labels. The quality of the strain estimates was assessed by using the signal-to-noise ratio and contrast-to-noise ratio, which are metrics commonly used in strain elastography. For the first experiment, we created our own ultrasound simulation dataset, which consisted in 160 image pairs. Each simulation consisted in a 3D rectangle containing a single circular inclusion with a randomly assigned diameter and position. The Young's modulus of the inclusion was also randomly assigned in the target inclusion. The Young's modulus was either set to 8, 15, 45, or 75 kilopascal, and the backbone was always set to 25 kilopascal. A different actual compression was randomly assigned to each phantom and represented between 0.5 and 4% of the phantom total length. The geometry and mesh of each phantoms were defined in MATLAB. The tissue displacements were estimated by finite element methods using the partial differential equation toolbox from MATLAB. And finally, we used the filter software to generate the ultrasound images. Concerning the ultrasound probe parameters used in filter, we set the probe central frequency to 7 MHz with a sampling frequency of 40 MHz. We also added white Gaussian noise on the images to increase the robustness of our network to noise. The figure on the left shows actual strain estimated from 3 different ultrasound simulation data pairs. The average contrast-to-noise ratio and signal-to-noise ratio score from the testing partition, which consisted of 30 image pairs, are displayed in the table on the right-hand side. We can see that our method gives very similar signal-to-noise ratio and contrast-to-noise ratio to the overwhelm method. Our results also indicate that our unsupervised method predicts strain estimate with a better contrast-to-noise ratio than the supervised model, which we believe is due to the regularization term of our loss function, which we only use for the unsupervised model. Concerning the in vivo experiment, we also created our own dataset, which consisted of images of the arm of 3 human volunteers. The ultrasound data were acquired using a research Cepasonics ultrasound system equipped with a 10 MHz linear probe. The images were reconstructed by using the DLN sunbeamformer produced by the Supra toolkit. Our experimental protocol consisted of acquiring sequences of images while slowly applying an actual compression on the volunteer's arm with the ultrasound probe. In total, 1600 image pairs were used to train our network. The figure on the left shows actual strain estimated from 3 different image pairs. The associated table shows the contrast-to-noise ratio and signal-to-noise ratio values respective to each case for our method and overwhelm. We also display the normalized cross correlation scores between image pairs to indicate the significance of the predicted displacement field. All images exhibit at least one or several blood vessels, which can either be seen in blue or red in the strain image. As you can see, our method exhibits comparable results to the overwhelm method over the 3 cases shown here. In this work, we've shown that our method exhibited state-of-the-art performance on both simulation and in vivo data. Also, our approach reached a strain prediction rate of about 13 frames per second in inference, which means we could potentially use our method for real-time processing of ultrasound data. To conclude, we believe the real-time inference of our network, as well as its ability to be trained without conscious labels, represent a great potential for the use of deep learning methods in ultrasound strain elastography. Thank you for watching. For more details on our implementation and experimental results, we refer you to our paper.